We are going to consider beryllium chloride, and we're going to look up the electronegativities for beryllium, which is 1.57, and chlorine, which is 3.16. I did these a long time ago, so I don't know if your table is the same. 3.16 minus 1.57 is 1.59. So this will make a compound called BeCl2, which you need to be able to write that. So I've written the formula, and I should have done that in the place provided, but I didn't. Write the electron dot structures. And this is going to be covalent because my electronegativity says it will be not very polar. And here's what it's going to look like. Then I'm going to switch colors for chlorines. This could also be drawn as either one of those would be correct. This would be a nonpolar molecule because it is in the general, it's linear. Nonpolar, it's linear. That's my Veciper shape. That's covalent. Blah, blah, blah. And then the intermolecular force for this, since it's nonpolar, will be London dispersion force. Next, magnesium iodide. This is going to be treated as ionic. It's going to be MgI2. If they're ionic, we are going to draw electron dot transfers. So I'm showing the electrons being transferred away from magnesium to iodine, and that's it. CO2, carbon dioxide, and CO2 is one that you should have built in the lab. And I'm going to do my math for this one, how many I need minus how many I have, then we'll divide by 2. So I've got 3 atoms, each needing 8. So I need 24. And for my have, I have 6 plus 6 plus 4 equals 16. This will equal 8 divided by 4, divided by 2 equals 4 bonds. And you can see that I now have 4 bonds, 2 double bonds. This will be a linear molecule. It will be nonpolar. And my intermolecular force, since it's nonpolar, will be London dispersion force. Sorry, I'm making a mess of this, but why can't I make this smaller all of a sudden? Okay, let's go back here and see if I can make this. There we go. Now we're doing nitrogen. Don't forget nitrogen is diatomic. Nitrogen has 5 valence electrons. My next nitrogen has 5 valence electrons. This would give me a structural formula like this. This is linear. It is nonpolar. And its intermolecular force would be London dispersion, because all nonpolars are London dispersion. I don't know why I'm having trouble with this. Let me go like this, then this over here. Okay. Next, let's try our silicon tetrahydride. Silicon tetrahydride is SiH4. Silicon, which is right under carbon, will be bonded to the hydrogens like this. This is a regular tetrahedron, so it's tetrahedral. It is nonpolar, and will have a London dispersion forces. Next, we have arsenic triiodide. And for arsenic triiodide, we see arsenic is in group 5. Oops. And it's going to bind with 3 I's and another way to draw this would be AS that was supposed to be I. This is going to be the delta minus end and the delta plus end. So this is polar, and its intermolecular force will be dipole-dipole. And its shape will be trigonal, pyramidal. And I did my polarity there and there. Sodium nitride is ionic, and it'll be Na3N, which means you'll have 3 NAs and 1 N. N has room for 5 electrons. It'll have a 3 minus. Whoopsie. I didn't want to put those on there. Plus, plus, plus. Beryllium, boron. And then I've got a hydrogen, a chlorine, and a chlorine. Remember, this is an exception, and boron can have 3 bonding sites. This will be polar because it's not the same thing attached to each one. This is not hydrogen bonding, so it'll be dipole-dipole. And this will be my delta minus end. This will be my delta plus end. What else? Oh, my shape will be trigonal, planar. You should be able to look all these things up on your sheets. Hydrogen bromide, HBr, HBr, 5, 6, 7, and 1. This will be my delta minus. This will be my delta plus. This is linear, polar, and dipole-dipole. And the last one on this page, sulfur dioxide. This one's a little harder. Sulfur dioxide. Now this is a resonance structure, which means it can exist in two forms or written two different ways. So this exhibits resonance. And remember, neither of these is correct. And it exists actually as a hybrid of these. You have to draw both. This will be polar. Its shape will be bent. Now this one's got a little bit different bond angle because if you look at sulfur, there are 3 areas of electron density. So on your shape sheet, if you look up 3, it's going to have a 3 and 2 format. And I think your 3 and 2 format tells you your bond angle is 116 degrees. This will be also dipole-dipole bonding. I do have nicer keys available, but I didn't talk about them. So if you want to watch this, I'm sorry if it's not perfect.